Welcome to Pre-Calculus. Today we will investigate factoring polynomials by rational root theorem. We'll take a look at two examples. Our first polynomial function is f of x equals 5x cubed plus 19x squared minus 29x plus 5. I want to factor that polynomial, and the challenge with it is I really don't have access to direct factoring because it's a degree 3 polynomial that includes terms all the way up to the constant 5. So I got to come up with another strategy, and a good strategy for that is the rational root theorem. What the rational root theorem says is that if there is a rational root for a function, then its possible rational roots will be given as a combination of factors of the constant number, which in this case is this plus 5, over possible factors of the leading coefficient, which also happens to be 5. So what I want to do first is I want to just list out the possible rational factors, and then I want to test them using polynomial synthetic division. So I'm going to write here just some notation. I'm going to call these possible factors of the constant term p-values. So my p-values will be plus or minus 5. That's a factor of 5. So positive 5 divides out of 5, negative 5 divides out of 5. And 5 doesn't have a whole lot of factors. The other one is going to be plus or minus 1. I'm going to call the possible factors of the leading coefficient my q terms. And since that's the same value, I can record those same possibilities. The factors of 5 could be plus 5 or minus 5, also could be plus 1 or minus 1. Now, once I've listed out the possible factors, I want to arrange those as ratios or quotients of p over q. So as I list out all the possible rational zeros for the function, it's going to take this form p over q, and I really just want to write the possible combinations. So I'm going to take my p values, I'm going to put 5, and then first of all, I'll put the first numbers in each list. So it's going to be 5 over 5, and that could be positive or it could be negative, depending on the combination of signs. I'm also going to write plus or minus 5 over the second possibility for my q values, 1. And then I have one final possibility. I could have the p-value of, in fact, I got two more, 1 over 5. And then lastly, 1 over 1. So I do need to kind of reduce that list down to see if I have any duplicates. So I see that 5 divided by 5 is actually going to be 1. And so I won't need to include that last division, 1 over 1. And then I've got plus or minus 5, and then plus or minus 1/5. So that's my list of possible rational zeros. Now what I want to do with those is I want to start testing them using synthetic division to see which one of those is an actual zero or a root for this polynomial function. I always start with the first one in the list. So I've got positive 1 there. So I'm going to set up my division with a 1 in the corner, and then I'm going to record the coefficients. So 5 is x cubed, 19 coefficient on x squared, negative 29 is the linear coefficient, and 5 is the constant term. Now I'm going to start the process. I'll carry down the 5. I'm looking to see if this comes out to 0 at the end. If it does, then I know I have one of my rational roots. If it doesn't, I need to keep looking. So I'll multiply here. 1 times 5 is 5. 19 plus 5 is 24. 1 times 24 is 24. Negative 29 plus 24 is negative 5. 1 times negative 5 is negative 5. And that reduces to 0. So one of my roots here is going to be 1. So I'll start listing out here because I've found one of them. It's positive 1. If I wanted to write it in factored form, I would take it to the opposite sign. Remember that number in the corner is a solution. So the factor that would correspond with positive 1 is x minus 1. Now, once I have it down to a quadratic, if I were to reassign variables and powers, it would now be x squared plus 5x squared plus 24x minus 5. At that point, I've got some options. I can either try to factor this just using traditional factoring methods for a quadratic, or I can run the division again. But since we've reached the quadratic, let's attempt to factor it. So I'm going to put my two parenthesis groups for the two binomials. I see my leading term there is 5x squared, so I know I have to have a 5x and an x to get a product of 5x squared. And then I see that the constant term is -5, so the numbers have to be 1 and 5, positive for one, negative for the other. And I see that the one that's going to work for us is going to be x plus 5, 5x minus 1. So if I just check that again by FOIL, first term we already checked, 5x times x is 5x squared. The outer term 5x times 5 is 25x. Inner term -1 times x, -1x. And that's really what I wanted to check. That sum is 24x, which matches our middle term there. And then the last term, I think we've already checked, is -1 times 5, -5. So that once you reach a place where you can factor the quadratic, you can do so. And real quickly, I'm going to set each of those equal to 0 and solve. So from the x plus 5, we get the solution x equals -5. And from 5x minus 1, if I set that equal to 0, I'm going to get a fraction 5x equals 1, which is going to give me a solution or a root. X is a fifth. So I'm going to put these roots in least to greatest order. So -5, 1/5, and then our original one that we discovered with synthetic division, 1. So notice that each of those rational roots, -5, 1/5, and 1, are actually represented in my list of P over Q values. So not all of my P over Q values make it into the roots list, but all of my roots are represented by those possibilities. Last thing just to note, I can use this for the factorization. So factorization of this polynomial is x minus 1 times x plus 5. Just pull in those factors from below, and then 5x minus 1. So that's an example of a degree 3 polynomial. Let's look at an example of a degree 4. So here I've got 2x to the power of 4 minus 9x cubed plus 7x squared plus 9x minus 9. Notice this is a larger polynomial. So in order for me to get to a place where I can factor a quadratic, I need to run synthetic division twice. Well, let's get started with our P and our Q values. So my P values, again, are going to come from the -9. So that could be factors of 9, plus or minus 9, plus or minus 3, and plus or minus 1. So notice I'm just listing out the possible factors of that constant term. I'm going to do the same for the leading coefficient, which is my Q value. Those come from the leading coefficient 2, so it could be plus or minus 2, and then plus or minus 1. So my possible P over Q values, I want to list them out. We'll start with just the way we've listed them here in our initial analysis. So I'm going to put 9 over 2 and 9 over 1. So I'll just vary the denominators to begin, and I'll put plus or minus for each. Then I'll go to 3 over 2, comma 3 over 1. And lastly, 1 over 2, 1 over 1. And notice it's a longer list because of the factors that I had in the P and the Q terms. So from my constant and from my leading coefficient, I've got more here because there's more factors involved in those numbers. So let's start. One thing that I often do is I begin with 1. So that's how I'm going to begin here. Last one I started with the first one in my list, and that may be in fact the factor, but just to try the easy thing, I'm going to put 1 in my corner number. And again, that's coming from this last plus or minus 1 over 1. So let's write out my coefficients for the polynomial. So it's going to be 2x to the 4th minus 9x cubed plus 7x squared plus 9x minus 9. So here's our first investigation. I'm going to drop the 2 and then multiply. 1 times 2 is 2. Negative 9 plus 2 is negative 7. 1 times negative 7 is negative 7. 7 plus negative 7 is 0. 1 plus 0 is, or I'm sorry, 1 times 0 is 0. 9 plus 0 is 9. 1 times 9 is 9. So we got lucky in this case. It did reduce down to a 0 remainder. And I found one of my rational roots. So I'm going to record it here. The root that I found is 1. And now I want to run the process again. I could put the factor that comes from that would be x minus 1. So remember, the 1 itself is a solution to that factor if I set it equal to 0. So I want to run this again. Let's try, we used 1 one time. Let's try 1 again. You never know. It could be that I've got a multiplicity 2 or something. So we'll put 2, negative 7, 0, and 9. So I'm just starting with my quotient for the second division. Put my division line, drop down the 2. So 1 times 2 is 2. Negative 7 plus 2 is negative 5. 1 times negative 5 is negative 5. 0 plus negative 5 is negative 5. 1 times negative 5 is negative 5. 9 plus negative 5 is 4. So you can see it didn't work. So what I'll do is I'm going to erase and I'm going to run it again. And typically what I'll do at that point is I'll switch the signs. So if I tried positive 1, now I'm going to try negative 1. Carry down the 2. Negative 1 times 2 is negative 2. Negative 7 plus negative 2 is negative 9. Negative 1 times negative 9 is positive 9. 0 plus 9 is 9. Negative 1 times 9 is negative 9. And that reduces to 0. And so I see my second rational root is going to be negative 1. So I'll just rearrange there so it's in least to greatest order. And at that point, what I've got is after a second division, this is reduced down from a degree 4 to a degree 3, now to degree 2, it's a quadratic. So my quadratic that I'm looking at is 2x squared minus 9x plus 9, and that I can try to factor. So let me bring my parentheses, and I'm going to write 2x and x. And I need to place factors on the inside here so that it adds to negative 9. Now it's multiplying to positive 9, so I see that both of those factors need to be negative, and I think that if we put minus 3, we should be good to go. Let's check it. So first terms there are going to multiply to 2x times x, 2x squared. And that's correct. Outer terms, 2x times negative 3 is negative 6x. Inner terms, negative 3 times x, negative 3x. And this is what I really want to check, is that sum. Negative 6x plus negative 3x is negative 9x. So that checks out. And then the last terms, negative 3 times negative 3, 9. And that's matching my quadratic. So I see that I've got 2 good factors there. I just need to solve them. So I'm going to set them equal to 0. I'll add 3 and divide by 2. And that gives me one of these roots, x equals 3/2. And I can see that is definitely in my possible factors right there, 3/2. In fact, my 1's are there as well. Let's solve the last root here. So I've got x minus 3 equals 0. Set that other factor of the quadratic equal to 0, add 3/, and immediately we see that x equals 3. And I can see that one is also in my list of possible rational zeros. So again, every root that I get that's a rational root will be represented in my list of p/q values. Not every p/q value will be a rational root. Let's finish the factorization since we've done that work. So I had the factor x minus 1 from the first division. From the second division, -1 would give me the root x plus 1. And then I had two other factors from the quadratic, 2x minus 3 and x minus 3. So not only can I find rational roots, I can also factor polynomials by using this process. Well, thank you for joining for this investigation of factoring and finding roots of polynomials using rational root theorem. See you soon.